Hey Cal 3 class, we're going to take a little stroll down memory lane. We got a 3D solid here, and we got an oval in the XY plane, or ellipse I should say, in the XY plane, and then that same ellipse up above it with the height of that upper ellipse going back and forth between 0 and 4. Okay, so 0 all the way up to 4. Now, why am I showing you this? Because I want you to recall that how do we get volume? Well, one of the ways that we could get volume from these right, they're basically like prisms. When we have a right prism, when we have a base that has some area A, and then we raise up to the parallel version of that base, perpendicular with a perpendicular angle here. The volume of this is just the area of the base times that height. So the idea of what we're going to do in this section, we're going to use double integration to find area, not volume. We've been saying, all right, well, the double integral, if a single definite integral gives us area, then the double definite integral is going to give us volume. Well, yes, it is. It does. It does give us volume, always. No matter what, it gives us volume. But what happens if I multiply the area times the height here, and I'm going to zoom in on this so you can see, and my height is 1. What's the volume of this, and what's the height of this? Well, let's say, hypothetically, that this volume is 5 pi units. Right, I know that's not right, but I'm just saying hypothetically that the area of the base was 5 pi units. Well, what are we multiplying by? We're multiplying by 1. We're multiplying by the height of the perpendicular nature between the base and the top, and it's parallel to the base. So we just multiply by 1. We multiply by the height. Well, the height being 1 makes that product of the area and the height equal to the area. So the volume equals area times height, area of the base times the height. But because the height is 1, the volume equals the area. And so we use that in this section where we're finding area with double integration. Notice we're doing the area is equal to the definite integral that we've been setting up, dA, but there's no integrand. There's no function here. But remember, the way that Riemann sums worked is we multiplied the differential times the integrand. Well, that would be, in this case, 1 times dA. So our integration, our function that we're finding the volume under is the function z equals 1. So that would be right back to what we saw before with those parallel shapes with a height of 1 between them. So whatever we find underneath it for the area, we're multiplying by that 1 to get volume, and we're getting the same. The volume would be the same as the area because the function that we're integrating is 1, the unit function. So it does still give us volume. It's just that the volume of this region will also be the area, and we're making use of that to help us find area. Okay, so I want to find the area bounded by these two parabolas. We saw this last time when I was setting up an integral for you. It's just our integrand was 3y. Well, now I'm going to make it just 1. So this is my upper function, this is my lower function, just like it was last time. It's just when I set up my integral, I'm going to set it up to be 1 dy dx. All right, this is the lower value of y, this is the upper value of y. I don't have the 3y in there anymore. I just have 1. And now when I do this, I'll integrate, I get y, I plug these in. Notice when we plug this in for y, we get this minus this. So 2 plus x squared minus 3x squared, that's where the negative 2x squared is coming from. And now we integrate with respect to x over that region. The antiderivative here is going to be 2x cubed over 3. All right, plug in 1 for the first one. I'll have a 2 and a negative 2/3. Plug in -1, I'll have minus -2, which would be plus 2 minus, I'm subtracting because of the integration, but I'm subtracting also because of the definite integration. So it's minus a negative 2/3 and subtracted from the positive 2/3. That would be a plus, negative plus, negative, it would actually be minus. So we get 2 minus -2, that would be 2 plus 2. And then we get negative 2/3 minus positive 2/3. Again, that's a negative going in, so it's changing it to a plus, but we subtract the lower value from the upper value. So we'll get a positive 4 minus 4/3. So that's 8/3 square units is the area. Okay, so again, if I make my integrand 1, this is 8/3 square units, but it's also the volume over top of that region that we just saw in the last picture. And if I had a plane above it that's parallel to the XY plane, 1 unit up. So just imagine this shape with a plane 1 unit up. That's the volume underneath that plane above that shape. It's equal to the area of that shape. It's just, it would be 8/3 cubic units for the volume. So again, a double integral over a region gives us volume. It's just because the function is 1, the volume equals the area. So we're taking advantage of that and using coming up with a way to find area. Okay, now this is a calculus 1 problem. Find the area between these two curves. Well, how do I find the area between these two curves? Between -1 and 1. I take the upper minus the lower. So this minus this, between those I set that up integration, and literally I would start this problem from here. So when you're doing these in your homework, if you want to set up with a double integral and do the work, that's fine. But just literally you did this in calculus 1. So if you want to do these as like a review of calculus 1, go for it. All right, we're just using this section is called applications of double integration, and this is one of the applications is using it for area. But we already did those with in calculus 1, find an area between two curves. So you can do it either way for me, and that'd be perfectly fine. All right, average value of some function over a region. So if this looks familiar to you, it's because of calculus 1 we did average value. All right, it's just that instead of 1 divided by area, it's 1 divided by distance, because again we were 1 dimension less. So 1 dimension less than the concept of area is the concept of distance. So this b minus a, that's just the distance between these 2 points. All right, and the average value, you remember these f of x, that's the height of this thing. So the height of this, the average height over these regions. So notice as I'm moving to the right, the function's going down, and the average value, that horizontal line, is shrinking. All right, if I bring it back, now we're going higher. We're stopping up here, and we're always above the x-axis, and that average value gets higher. All right, it starts coming back down right in there. All right, so we're losing height at that point. Okay, so we get like a highest average height right there. It looks like when we're coming up with our maximum average height that we could come up with. Looks like 3 is the highest we could get, unless we bring this up, and then we can go up higher. Keep squeezing that in towards 4. We can keep getting higher and higher. So anyway, there's the kind of link to that formula that we've seen that formula before. It looks very similar to what we're dealing with on this page. Okay, so very similar to what we're dealing with. Let me give you a visual of what it would look like in 3 dimensions. So this is the greatest drawing of what this is, but we've got this region defined down in the XY plane. That's this black curve. That's our domain. All right, and So that's like this thing here. So we're going out -2, +2, and the average value is this height right here. Okay, and this is a parabola, and it touches at 4, and it hits at 2, and -2 on x and y. Well, that's what we have here. You know, it's going up to 4 in z. It's hitting at, if you kind of look here, it's hitting at 2. There's 3, 4. It's hitting at -2 in x and y. And so, you know, we're looking at like that here. Okay, but because we have 3 dimensions, when we come out this way, instead of it's, you know, we've created a, you know, a rectangle that has the same area. And what I mean by that is the area of this rectangle, this black rectangle, is also equal to the area underneath the curve of that parabola. Well, what we've done here is the volume over top of that circle under the paraboloid is equal to the volume of that cylinder now. Because we have a circular base, we have a cylinder. So the average value is still the same concept. It's like this, you know, this plane that's parallel to the xy plane. So like z equals some number. And it's the volume underneath that plane, but above the same shape, the same domain, has the same volume as the volume under the surface of that same region. Okay, now this would be for any shape. This is not just a paraboloid. I'm just doing it because it looks exactly like this. I was just showing you something that looked like that, but this could be any shape, and this would be something that is directly above it with that exact same shape. And the height of that would be the same as the volume underneath whatever surface that we had. So if we did this same concept, find the average value of this, we had 5y over that area that we had before, this intersection of those two parabola. We can do that the same way. We found the volume underneath it to be this. Okay, we've already done that work, and we found the area just in the last problem to be 8/3. So how do we do it? Well, again, look at our formula. 1 divided by the area. Since our area is a fraction, we could just multiply by the reciprocal of the volume. This is volume. This is 1 over the area. So how do we do it? We flip and multiply, basically. So 1 over 8/3 is the same thing as 3/8. 3/8 and 8/3 is will reduce, so we get 56 over 8, which is 7. All right, and so what does that mean? Well, let's go back to that picture. Let me just do like this, and go back to this picture. If we made a plane, let me use green. If we made a plane here, there's 15, so let's say that 7 is right there. So if we made a plane parallel to the xy plane that went through this number 7 right here, alright, and where that thing intersected this parabola shape, alright, it basically would just be the parabola shape. The intersection of these two parabola shapes, I should say. Something like that. So that's z equals 7, but directly above the parabola shape down here below. Alright, this shape right here. Okay. What do we get? We get this thing that has, it looks like this, the intersection of those two parabolas on the bottom and on the top. drawing this with a computer mouse, so this is not going to be the prettiest thing you've ever seen. But hopefully you'll get the idea. It's that same shape, the intersection of those two parabola down in the XY plane, but up on top as well. And it's just a height. This is 7 units tall. Alright. So if we made that area on the bottom, that same area on the top, and multiplied it by 7, because that's the height, that's like the picture that we saw before with those two ellipses right on top of one another, it would have the same volume as this that goes up. It tilts up. It goes all the way up to 15. So it's down at 0 here, but it goes all the way up to 15 here. So it's got higher volume on the upper end and lower volume on the end closer to the origin, this end down here. These volumes would be the same. So that's a visual of what we just found with the work in that problem.